Welcome to In 5 Minutes. Our topic is tensile test of ductile material. Before we start what is tensile test, let us first study something about ductile and brittle material. Now what is ductile and brittle material? Ductile material, a material which undergoes extensive deformation under the action of loads before failure is called as ductile material. Example is mild steel, aluminium, copper and many other material, etc. Brittle material is a material which undergoes little deformation under the action of loads before failure. Example is cast iron. Mechanical properties of most of the materials, whether ductile or brittle, can be easily studied by a test called as tensile test. Now, tensile test. What is tensile test? Tensile test can be carried out on a standard specimen of the shape as shown in a figure of diameter d and length L by applying tensile load on its axis. This test is carried out on a machine called as universal testing machine. The specimen is loaded between the two jaws of the machine and by hydraulic means loads are applied so that tensile load is applied on the specimen. As the load are applied, we can measure the two properties. In the tensile test, as the load is applied and gradually increased, we can continuously measure properties which is sigma is given by P upon A, where A is the original cross-sectional area. We can also measure the strain E, which is given as delta L by L. The tensile test is carried out on the specimen until the specimen fails or breaks. From the start of test up to the failure, we measure the stress and strain and we plot it on a diagram called as stress-strain diagram. We plot the stress on y-axis and strain on x-axis. This curve is a typical stress-strain curve for any ductile material. Initially, when no load is applied, we have stress is equal to 0 and strain equal to 0. It is denoted by point O. As the load is gradually increased, we see that the stresses is developed in the specimen and the specimen elongates as shown in a figure delta L. So the stress-strain curve increases in this fashion. As load is gradually increased, both stress and strain increases. It has been found that the material elongates and the stress is directly proportional to strain up to some load. That is, the ratio of stress and strain is constant. This fashion continues up to point P. The material is said to be in an elastic state. Elastic state means that when the applied load is removed, the material again go back to its original size and shape. As the load is gradually increased, we see that both stress and strain increases and the material elongates as shown in a figure. From point O, the stress is directly proportional to strain and it has been found that the ratio of stress and strain is constant. This fashion continues up to a point called as proportional limit. The material is said to be in an elastic state. Elastic state means that when the applied load is removed, the material again go back to its original size and shape. Now beyond point P, there is a small region up to point E where the material still exists in elastic state, but the stress and strain is no more linear. So point E is called as elastic limit. Even if the load P is removed, the material won't go back to its original size and shape. That means there will be permanent set of deformation induced in the bar or specimen. Now this plastic region is also called as yielding region. Yielding has a characteristic that there is a considerable increase in strain in this region and negligible increase in the stress. Now the curve follows an S path. The point of maximum stress on this yielding region is called as upper yield point, whereas the point of lowest stress in this yielding region is called as lower yield point. Upon further increasing the load beyond point Y2, there is a considerable increase in load for further straining, and this is due to the phenomena called as strain hardening. This curve again rises up and point U is called as ultimate tensile point or ultimate tensile strength of a material. Ultimate tensile point is the maximum stress encountered in a tensile test of a material. Beyond point U, ultimate tensile point, we see that there is a localized reduction in the cross-sectional area at the weakest point of the material. This is called as necking. This continues until the material finally breaks. Now due to the reduction in the cross-sectional area, the required load to further strain decreases and eventually the material breaks, that is, it breaks into two pieces. The failure which takes place for a ductile material is called as cup and cone failure, meaning that one piece of the broken specimen has a cup shape and another has a cone shape. So we see that up to point E, the stress strain curve is in the elastic region, whereas beyond point E, the stress strain curve is in plastic region. If we consider the ratio of the strain of the plastic region and strain of the elastic region, if we plot the stress strain curve to true scale, we'll find out that the strain or delta L of the plastic region and the delta L of the elastic region is such that the ratio of its deformation is in the range of 100 for most of the ductile material. With this, our topic is over. Thank you.